Hello, welcome to this lesson in the Linear Algebra Tutor. We've taken a tremendous journey up until this point in time in our linear algebra studies. Now we're going to talk about something that's absolutely central to all topics that you'll find in any linear algebra course. That's called the inverse of a matrix. In this lesson we're going to concentrate on finding the inverse of a 2x2 matrix because it's very easy to do and I can illustrate a lot of the properties of inverses to you very easily. But in the next section we'll learn a different way to calculate the inverse of a matrix that you can apply to any size matrix. And so we'll get to that later, but here we're going to focus on 2x2 matrices. First of all, what is an inverse of a matrix? I could just jump right into it, but I'd like to draw an analogy back from algebra. Remember back from algebra, you might know how to solve 3x is equal to 9. How do you do that? Well, we all know you divide the left hand by 3 and the right hand by 3, but really what you're doing, instead of thinking of it as division, think of it as we're multiplying the left by 1/3 and we're multiplying the right also by 1/3. Wouldn't you agree that this is basically what we're doing? And so on the left-hand side, what's happening on the left-hand side is the 1/3 is kind of canceling, so to speak, giving you a 1 on the left-hand side in front of the x. And on the right-hand side, we're just left with what we get. So x is equal to 3. That's something that you have been using over and over and over again in algebra for a long, long time. But what you may not realize is that the number 1/3 we say is the multiplicative inverse of the number 3. So if you're given a number, you can find the inverse of that number, which in this case is just 1 over the number, such that when you multiply them together, you just get the number 1. That's the definition of an inverse in general. So for instance, what I'm doing here, I take the number 3 and I multiply it by 1/3 and I get the number 1. So this we say is just a number. And this is what we call the inverse of this number. And the definition of the inverse of a number is it's whatever number is such that multiply it by the original number and you get a 1. So that's kind of what the concept of an inverse is in terms of numbers. Now we want to extend this concept to linear algebra to matrices because we want to figure out how to calculate the inverse of a matrix. I'll explain the application of that a little bit later, but first let's concentrate on just calculating or figuring out what it would be. So ultimately what we want to do for matrices is if we're given a matrix A, we want to figure out what matrix can we multiply it by. We'll denote it by a -1, that means inverse, to give us, well obviously it's not going to give us a number 1, it's going to give us an identity matrix. Remember we talked about an identity matrix. So this guy is just some matrix. This guy is the inverse of this matrix, and this guy is an identity matrix, which might be like 1, 0, 0, 0, 1, 0, not an, yeah, 0, 0, 1. Basically, an identity matrix is where you have 1s along the diagonal and 0s everywhere else. So you see the direct extensibility from numbers to matrices. Here we're trying to find an inverse so that when we multiply, we just get a single number 1. Here we're trying to find a matrix so that when we multiply it by the original matrix, we get a diagonal array of 1s with 0s everywhere else. Because that really is an identity matrix. Remember, we talked about the concept of an identity matrix. Identity matrix behaves like the number 1 in terms of numbers because I can take a 3x3 matrix and multiply it by its identity, I'm going to get the same thing back. So it kind of effectively behaves like the number 1 if you think about it in terms of numbers. So I don't want you to get too worried about the -1 up here. It's not really raised to a -1 power. This is just how we denote the concept of the inverse. All right. Now for a 2x2 matrix, there is a shorthand way of calculating this inverse. I'm not going to prove it to you, but if you have a matrix A, and there's numbers here, but I'm going to label the numbers A, B, C, and D. So A, B, C, and D can be any number you want because it's going to be a 2x2 matrix with numbers. Then the inverse of this matrix is 1 over A, D minus B, C multiplied by the matrix D, -B, -C, and A. So this is the matrix you start with. This is how you calculate its inverse. What you have out in front here is a number there that you're going to get here. And then this is just a rearrangement of the original elements of the matrix here with some negative signs. And so you get it all, you multiply it all out, and you get what we call the inverse of the matrix. Now this is only valid for 2x2 matrices. It's a shortcut way. In the next lesson, I'll teach you how to take inverses of larger matrices using a more general technique. But for here, it works just great. So let's go ahead and do a quick example. Let's say we have a matrix 1, 2, 1, 0, and we want to calculate its inverse. All right, so what we say is the inverse of the matrix is going to be equal to 1 over, remember this is A, B, C, D. So it's 1 over AD, this is A and D, 1 times 0, minus B times C, 2 times 1. Right? So you can think of this as being a crisscross. So it's this times this, as you're forming an X, minus this times this. For those of you who have studied a little bit of matrix algebra before, this is basically the determinant on the left-hand side right there. We're going to talk about determinants a little bit later, but just to kind of refresh your memory a little bit, if you're seeing something that you may have studied in the past, what's happening down here is basically the determinant. Now we're multiplying this by the matrix. D goes here, D is 0. Negative B, which means negative 2, negative C, which means negative 1, and down here we get A, which is 1. So basically what you do is you stick negatives on this diagonal elements and you switch these guys around, basically is what's happening. So this inverse that we're calculating is going to be 1 over, this is going to be 0 minus 2. So what you end up having is negative 1/2 times 0, negative 2, negative 1, 1. Now, anytime you have a matrix like this with scalar multiplied on the outside, you can just do the multiplication, and negative 1/2 times 0 is going to give you 0. Negative 1/2 times this will give you 1. Negative 1/2 times this will give you 1/2. Negative 1/2 times this will give you negative 1/2. So what we have is 0, 1, 1/2, negative 1/2. This is the inverse of matrix A that we started out with. You see, it's a process that you can't just look at like you can with numbers and figure out what the inverse is. You have to actually do a calculation. Now that we have the inverse, this is what you would circle on your exam if the question was calculate the inverse of matrix A. But we want to go a little bit deeper and prove to ourselves that this really is the inverse. All right. So let's first start out by taking matrix A and multiplying it by its inverse. Let's see what we get. Matrix A is 1, 2, 1, 0. Inverse of matrix A is 0, 1, 1/2, negative 1/2. Now you need to remember how to multiply matrices. Over and down, over and down, over and down, over and down. That's what you do, right? So for the first element, over and down, 1 times 0, 0, 2 times 1/2 gives us 1. And then for the next element, over and down, 1 times 1 gives me 1. 2 times negative 1/2 is going to give me negative 1. So when I add those together, I'm going to end up with 0. And then to get this element down here, over and down, 1 times 0, 0. 0 times this gives me 0. And then when I go over here, down 1 times 1 gives me 1. 0 times this gives me 0. So I'm going to end up with a 1. So notice that I get an identity matrix, I sub 2. So when I take the matrix and I multiply by its inverse, I'm left with an identity matrix. That's exactly what the definition of an inverse is. So we know we calculated it right. Let me show you real quickly though. Here we have multiplied the matrix times its inverse. What happens if you take the inverse and multiply by the original matrix? Remember we said in general, when you have matrix multiplication, if you flip the order of the multiplication, you almost always will get a different result. So let's just see what happens here. In this case, the inverse is 0, 1, 1/2, negative 1. And the matrix is 1, 2, 1, 0. So what's going to happen when I do that? So if I go over and down, 0 times 1 is 0, 1 times 1 is 1. And if I go over and down here, 0 times 2 is 0, 1 times 0 over here is 0. 1/2 times 1 gives me a half, negative 1 times this one. So when I go over here, I have, well, you see, I notice a problem right away. Actually, whenever I wrote the inverse down, it should be negative 1/2 here. This is the inverse of the matrix that we had here. This is the original matrix. I noticed a problem because I'm kind of giving away the punchline. It doesn't matter the order in which you multiply these. You still get the inverse in either case. So let's go and multiply this times this. I'll have a half from here, and I'll have a negative half from here. It'll give me a 0. And over here and down, 1/2 times 2 is 1. This times this is 0, so I get a 1. So this is also called an identity matrix. All right, and so the point is, in general, when you take any two random matrices and flip the order, if you're able to multiply them, you're probably going to get something different, right? The order of the multiplication of general matrices, it does matter. But in the case of multiplying a matrix times its inverse, you can do the multiplication either way, and because the inverse matrix is a very special animal. So when you take the matrix and multiply it by its inverse, you get the identity matrix. When you take the inverse and multiply it by the original matrix, you also get the inverse. Something I just wanted to let you know. The order does not really matter. The other thing I want to tell you, a definitional kind of thing that you'll see in books, is if the matrix does have an inverse, it's going to be called non-singular. It has, or let me do it like this. Instead of saying it has an inverse, I'll say the inverse exists. But sometimes you try to calculate the inverse and it doesn't actually work. So you have what we call a singular matrix. The inverse doesn't exist. And that's totally different than with numbers. With numbers, I can always find a multiplicative inverse, right? I mean, we can solve equations all the time by multiplying by fractions and get rid of things and make them equal to 1. But for matrices, sometimes when you try to get the inverse, you can't. It doesn't work. So let me show you that. When that happens, it's called singular. Singular means kind of singularity. Things go to infinity. That's what singularity means, or singular. Let's do a quick example of something like that. So if I have a matrix 1, 2, 1, 2, like that, and I want to calculate the matrix inverse. So if you remember the definition, let me switch colors here. The definition for a 2 by 2 matrix of an inverse matrix like this is 1 over AD minus BC times the matrix D minus B minus C and A. That's just to remind you of what it is. So let's go ahead and calculate it. What I'm going to have here is 1 over A times D, 1 times 2, minus 2 times 1, B and C, 2 times 1. And then inside of here I'll have D, which is 2. This guy will be a 1, negative 2, negative 1. So basically we put negatives there and we switch the result of that. D switching with A. So let's go and calculate it. We have the inverse, which is going to be equal to 1 over 2 minus 2 gives me 0. And I don't even need to go any farther. I don't need to put anything here. I have a major problem. When I try to calculate it, I get an infinity in the result. When I try to calculate the inverse of this matrix, because of the way the matrix elements were constructed, I cannot find an inverse. So we say that this guy is a singular matrix. We'll say A is a singular matrix. Means its inverse doesn't exist. Now this is how it shows up in a 2 by 2 matrix, that you get a 0 here making an infinity. But as we learn how to take inverses of larger matrices, I'll show you what to look for to figure out if your matrix is singular or not. The big thing I want to teach you here is that for every matrix, you can try to calculate what we call the inverse. Sometimes you can't, so you call it singular. Most of the time that you can, though. And the property of an inverse matrix is such that when you take that inverse and you multiply it by the original matrix, you simply get an identity matrix as a result, which means in the matrix world, you're getting the number 1 back expressed as a matrix. That's everything I want to talk about here. We've limited this discussion to 2 by 2 matrices on purpose to keep the concept simple. The next section, I want to teach you how to calculate inverses of larger matrices, because the concept of an inverse will be incredibly useful as you go through linear algebra solving problems. So let's go on and learn how to calculate inverses of larger matrices.